Hello everyone, I am Subhadeep Sahu and today I am going to present our research paper Synchronous Evacuation for Dual Virtual Machines under Disaster Risks. This paper belongs to TSP 2020. So, in recent years, the information technology and telecom industries are evolving towards an era of network virtualization, which enables internet service providers to flexibly provision heterogeneous virtual networks over shared substrate networks. We can say a VN generally consists of virtual nodes and virtual links, which and the virtual nodes are realized through virtual machines, and the virtual links are mapped on one or several successive substrate links with customized bandwidth. As more and more applications are carried by virtual networks, the survivability of virtual networks becomes a critical challenge under large scale disasters scenario. With severe risks, a VN should evacuate the threatened virtual machines out of the DRG as soon as possible. The virtual network evacuation involves two important operations. One is VM reconfiguration and another is VM live migration. VM live migration has two different fundamental techniques. One is pre-copy and another is post-copy. For pre-copy, it first copies all the memory pages and disk storage to the destination server while the VM is still running on the source server and it is generating modified pages. But for post copy, it first suspends the source VM and then transfer its CPU state to the destination server, and then it resumes the destination VM. After that, finally, it transfers all the memory pages and disk storage to the destination server. So in our problem statement, we can say given a wide area network, we assume that there are two substrate nodes covered by a DRG. In this case, a VN with dual virtual machines inside the DRG has higher destruction probability than those with single VM inside the DRG. The goal of this strategy is to minimize the evacuation time period for each dual VM as well as the entire time period for completing all dual VM evacuations. We model our network, model our substrate network as GS, and here VS is the set of substrate node and ES is the set of substrate link. Say a substrate node has certain amount of available node resource and a substrate link has certain amount of available bandwidth capacity. A VN is modeled as GV. So for simplicity purpose, only one DRG is assumed existing in GS at the same time, which covers two substrate nodes as well as the adjacent links. Our proposed strategy, named as Synchronous Evacuation Strategy for Dual VMs, ACDV, includes two phases. One is VM reconfiguration, another is VM live migration. So for VM reconfiguration, we have two constants. One is the candidate substrate node and links should have enough available resource capacities to accommodate the remapped virtual nodes and the links. And a virtual node can be mapped only on one substrate node. Also, a substrate node can host only one virtual node from the same VM. So for optimization purpose, we narrow the solution space by limiting the distance between the candidate substrate nodes and the non-threatened virtual nodes of GV. Then we choose the substrate nodes with minimum total distance for all the remapped virtual links of GV. Okay, but for then we come for VM live migration, we utilize post copy live migration technique. First, a basic migration bandwidth is set for all VMs to be migrated according to the link capacity of GS, which can limit the maximum migration time for each VM. Then a pair of shortest paths with the basic migration bandwidth is calculated for each dual VM, which also can prompt as many VM as possible to evacuate at the same time. After that, the migration bandwidth of each virtual machine is upgraded to the upper bound along its migration path and migration is conducted. Then we calculate the migration ending time of a virtual machines by using equation 1. Here dmij is the data amount to be migrated and bmij is the bandwidth assigned for this migration. Then we adjust the bandwidth for each VM of the dual virtual machines according to equation 2, so that there will be the synchronization between those virtual machines, and this can happens only when it reaches the downtime. So here we present the heuristic algorithm of our scheme, and you can see all the detailed steps of our heuristic algorithm is presented here. Then coming to the test topology, we have utilized NSFNet, and this has 14 nodes and 22 edges, and the DRGs are marked with shadows. Then we assume that each substrate node has enough storage and computing resources, and each substrate link has certain amount of bandwidth capacity, and the link capacities are 65 Gbps, 70, 75 and 80 Gbps. Initially we have injected 160 virtual networks in NSFNet. After that, uh, according to the DRG, we do the migration. For testing our performance, we have compared our performance with another baseline scheme named as Best Effort Evacuation for Dual VMs, BEDV. BEDV employs the same reconfiguration technique, but it has different migration scheme. For migration phase, BEDV calculates pair of shortest path and assign full available bandwidth along them. Okay, so here you can see the TET versus total evacuation time versus bandwidth, basic migration bandwidth. So for different substrate link capacities, all the TETs rapidly decrease according to when the basic migration bandwidth increases from the range of 0 to 4 Gbps, but it becomes saturated after 5 Gbps. So we set basic migration bandwidth at 5 Gbps for the rest of the simulation. Here we also compare our performance of average evacuation time and total evacuation time, okay, with BEDV. So we can say ACDV distinctly outperform BEDV, particularly under low substrate link capacity, because ACDV first guarantees an acceptable migration time for each virtual machines by a basic migration bandwidth. After that, the bandwidth is upgraded, and it can guarantee the synchronous migration for dual VM by adjusting the migration bandwidth in proportion. So the evacuation time cannot be prolonged. But for BEDV, only it finds the shortest path and then occupies all the available bandwidth. So it is leading to a long evacuation time for individual virtual network. Now coming to the total evacuation time, we can say ACDV can outperform BEDV in terms of total evacuation time. The reason is that ACDV prompts as many VM as possible to migrate at the same time, and BEDV tries to assign the maximum migration bandwidth for each VM, which particularly cause the serial style VM migration. So the performance of BEDV is worse than that of ACDV. In conclusion, we can say that we have studied VN survivability issue and proposed one scheme named as ACDV, and ACDV first reconfigures the threatened VNs out of DRG and then utilize post copy technique for the migration purpose, and our ACDV scheme can outperform the baseline scheme. Finally, we are really thankful to all the fundings listed here. Thank you very much. If you have any questions, you are welcome.